welcome to the Journal Club, everyone. Our first speaker today is Prakhar Bansal. He's a PhD student at the University of Michigan, and today he'll be telling us more about the difficulties with late-time solutions for the Hubble tension. Prakhar, thank you for accepting our invitation. The floor is yours.
Yep. Thank you. Thank you, Enrico, for the introduction. So, hi everyone. Today I'll be talking about our paper, which came out on Archive last month. It's titled "On the Difficulties with Late-Time Solutions for Hubble Tension." Here's the archive number and the QR for the same. And yeah, I'm a second year PhD at University of Michigan. My advisor is Dragan Hutrer. And a little bit about this work. So here we explore late-time solutions of the Hubble tension, and it's an idea which has been explored in the past. So some of this work has been like part of this work has been done in a few papers, but we wanted to clarify this more for ourselves. And in the process, we did some additional things which previous works haven't. So yeah, so that's why I hope it would be an interesting talk for you all. Okay, diving right into it, here's a little bit refresher from the grad school. How does a typical supernovae likelihood work? So on the here I have some equations, very simple ones. So this mu is the distance modulus as we know it, 5 log dl plus 25. Here dl is in 10 megaparsecs. And then what you can do is so these are the quantities which typically enter the likelihood. M app is the apparent magnitude, mu is the distance modulus, and capital M apps is the absolute magnitude. So this is the how I make the distinction between small m and capital M all throughout. And then I can plug in this mu, and then I get this expression. I can do a little bit gymnastics, and finally I arrive at this equation, right? And this equation has two key pieces. This H naught dl, as you can see, dl has an inverse H naught dependence already. When I multiply it with H naught, all the H naught dependence goes away. And what people typically like to call this is the cosmology dependent term, which depends on matter densities. If there's some dynamical dark energy element as well, then all that dependence goes in this term. And then the other term, the script M, this has two key ingredients. One is supernovae properties, which I'm using as a proxy for all the absolute magnitude dependence, and then H naught as well. So in a typical analysis, what happens is typically when you hear that supernovae are being combined with, for example, DESI or any other types of data sets, what they do is in order to not worry about Hubble tension, they marginalize over this whole parameter. So in some sense, we are being agnostic about the absolute calibration of supernovae, and we are just concerning ourselves with the magnitude of the or the shape of the Hubble diagram, which is in this term. But now, when we talk of Hubble tension, we have to consider the calibrations, right? So the next slide shows you how a typical calibrated supernovae likelihood works, right? So again, this equation holds M apparent equals mu plus MFs. Now, there are two key pieces from the data side. One are the low Z calibrators, which are Cepheids, and then Cepheids in the host supernovae, and then you have the high Z supernovae. And what each piece contributes to the likelihood is in these circles. So for the calibrators from the data side, you have the apparent magnitude. This is what our telescopes measure. And the distance modulus. These are independent measurements. So since these are low Z objects, so you can also calculate their distances independently. And then from the theory side, the only thing that goes is the absolute magnitude. Now, in most of the analysis, this is kept as a free parameter. So calling it theory is not completely correct, but I didn't want to make another category here. So I'm calling it a theory. But when I say theory, enters as a free parameter from the fit, which is derived from the fit. And then for high Z supernovae, from the data side, we only have the apparent magnitude. And then what you fit for is the cosmology, which is this mu Z, and then apps. So a bit more concretely, what happens is that here from the data side, since you have both the apparent magnitude and the distance modulus, the fit gives you absolute magnitude. This fit goes to the helps the other part, which is for the high Z supernovae, and this ultimately helps us derive this mu Z, which contains cosmology information, including H naught in this case, right? And this is how you typically get a measurement of H naught using just the calibrated supernovae. Okay. And then a key piece of assumption which goes in is that the you can use the same absolute magnitude M for all the redshift supernovae, right? And this is what really makes them standard candles, right? Because this is the assumption. And here the central theme of this work is we try to play around with this assumption just to see how much we are able to improve the fit to the data. Okay. And then before diving in, just a quick thing. So the data set that we use is the Pantheon plus shoe sample for supernovae, DESI, DR to BEO. And for CMB, we don't use the full CMB. We only use the geometrical information, the compressed CMB, which many papers have used, which is the shift parameters R and LA and the baryon density omega BH2. Okay. Now, how to present the problem? So there are two ways, and we have been using these kind of Hubble diagrams all throughout. So these small circles are the BAO points calibrated by Planck lambda CDM sound horizon. And here, to first tell or to depict how what the problem is, what we have done is we have taken the Pantheon plus shoes uh, calibration by the shoe Cepheids, and then we have applied that to all the points. So the triangle is the calibrator itself from the Cepheids, and then these squares are the supernova data points, and then you can see an immediate problem when we assume that the m to all the absolute magnitude is same for all these points. You can see that at the same redshifts, these points do not agree. Right, the BO points and the high Z supernova do not agree at the same redshifts when used with different calibrations. Now, of course, this can also be thought of as that if Pantheon plus Schu's sample tells me that the H naught is 73, I would expect the distances to be lesser. So that's one other way to think about it, right? So that's one analysis I can do. The other way to present the same problem is if I make a combined fit, right? So I consider all my data, which is BAO, CMB, and Pantheon plus shoes. But this time I allow M to be a free parameter. So I don't apply the shoes M to all the data points, right? And then I let the data decide what fit or what best fit M it prefers, right? In that case, we again have another problem, as you can see. So all these points are now the supernova points are calibrated by a joint fit to BO, CMB, Pantheon, and shoes, right? Now the best fit M that the shoes prefer is roughly like minus 19.25 with this error bar. But the fit of M, the best fit value of M that I get after this fitting procedure is roughly minus 19.40. So again, you can see an immediate problem. There's a these two quantities are 5 sigma apart, right? So what it tells me what the best fit M that all the data prefers, right? The BOCMB, the early time data prefers for the supernovae points to agree with them. That best fit M is 5 sigma apart from what shoes is actually seeing. Okay, so this is one other way to present the Hubble tension. And that's why you might find it commonly referred in literature that Hubble tension can also be considered as an absolute magnitude tension. And thus, a model, and here we also aim to find such model, a model which solves Hubble tension would, what it would, what we would want it to do is to give a best fit absolute magnitude M to the combined fit, which is consistent with the shoes Cepheids and doesn't have this 5 sigma deviation, right? And again, to give it away, it's not a trivial thing to do. So yeah, we tried some toy solutions and I'll slowly present them to you. The first thing which I want to tell what doesn't work is, and which part of makes the title of the paper is the issues with the late time solutions of the Hubble tension, is that a simple expansion history modification cannot work for this. So for example, we consider a very toy model here where we perturb the Hubble parameter using an extra free parameter. So this is H naught easy. This is your good old Hubble parameter. And what we do is we introduce another free parameter H naught E for the early time. So we assume some transition redshift and then we assume there are two Hubble constants. This can easily be modeled by some dark energy component, but here we just wanted to play around with the toy model to make our point. And then what you can see is, so again, this type of Hubble diagram with the gray is the lambda CDM model, and then the purple one is the model under consideration, which is H step. Here we have considered, so for this plot, I've considered the transition as 0.013 redshift. I'll talk about the significance of this transition in a couple of slides, right? And you can see the fit to the data improves, it doesn't improve, so to say, right? It's delta chi-square of just -1, right? And again, the same problem is there. So this difference here is M theory best. So from what the fit I get from the theory for the absolute magnitude minus the shoes fit. So again, one more crucial point about this plot is that for the Cepheids, it doesn't make sense to compare mu of the Cepheids to mu of theory because mu of theory doesn't enter the likelihood. So effectively, what we are plotting here is the distance is the difference of the best fit of M and the best fit of shoes. So in some models, we'll see that this thing actually, the Cepheid points actually agrees with the theory line, and then we can say, okay, there's a significant improvement to delta chi square. Again, all these are binned data points just to for visual clarity. In reality, we use the full data. We don't bin the data. Okay. And then here is again one more example with a W0 WCDM model. The story remains the same. There is slight improvement, which we believe is coming from BO fit, improving fit to BO and CMB. But as far as we are concerned, the M theory best fit still remains far away from M shoes. Okay. So these are the things which cannot work. Principally, a simple expansion history modification cannot work. So what type of solutions can work? Uh, there are couple of things we found. One is that if you allow for a break in supernova absolute magnitude, that significantly improves the delta chi square. So I can play the same game, but this time with the absolute magnitude. So instead of assuming there's one single absolute magnitude, I can assume there are two, right, which apply to separately, at some step redshift. Again, this is pure a toy model. I think if you go around and talk to supernovae people, they have a very high reason to believe that the evolution doesn't happen, or it's not that massive at least. But here we have also tried to, later on I'll show you a physical model which is somewhat tweaked, but it still works. Okay, so if I consider this case, then this we are calling as M-step model, and here at the same transition redshift, we get a significant improvement. This model just has two more free parameters as compared to lambda CDM. Again, it's a toy model, but the point is to show that it actually works. So if you allow for a transition in magnitude, then it works. Now, if I comment on the best fit values that I get from the fit, then it kind of helps us understand where this improvement is coming from. What essentially this model is doing is it is decoupling the Cepheids, which have a M measured for them, from the high Z supernovae, right? So the high Z supernovae, what happens is that the early time data, BO and CMB, forces the ME parameter, the early time absolute magnitude, just so that these distances can agree without messing up this absolute magnitude, right? So the Cepheids can be in agreement with what Schur is finding, and then only the high Z supernovae's absolute magnitude change, right? And so essentially, this is decoupling the two data sets, and that's how we can understand why this solution works so well. So it's trivial in that sense. The other thing that you can do is, on top of an M step, you can also allow the same H step I mentioned earlier. So this model we are calling H step plus M step. And the level of improvement is slightly higher, but it's more or less the same as far as these numbers are concerned. And again, here's the same story. The fit for the early time absolute magnitude is around minus 19.4, and this is around minus 19.25. So that's how it can stay consistent with both data sets. Okay, and then here is one more a similar flavor of model. So instead of H step, we consider W naught WA plus M step, and we see a similar level of delta chi square here. Okay, and now, as I mentioned earlier, does the redshift of where this step happens also matter? And the short answer is yes. And so here, what we have done is we have considered different step redshifts, and I'm plotting all the three models: M step, H step plus M step, W naught WA plus M step. And on the left, I'm plotting how much is the improvement in the fit, delta chi square. And we see that there's a clear peak at this redshift. This is the redshift point of around 0.013, where the last calibrator ends. So it further fuels a story that what essentially these step models are doing, or the best fit step models are doing, they're decoupling the calibrators from the high Z sample. Okay. Apart from that, there in these H step plus M step models and W naught W plus M step model, there is a somewhat less significant peak which happens at around a redshift of 0.15 as well. In the interest of time, I won't be able to go into the details of this. This is covered in the appendix of our paper. But what we believe is approximately happening here is this is an approximate compensation, not as good as this one, in which basically half of the supernovae tend to go towards the Cepheids. And that's why you see that the delta M of the, or the ME and M of the best fits are not that apart, 5 sigma apart. In this, they are 3 sigma apart. So yeah, it kind of depends on the sample, how many data points you have, and what are the error bars on them. But yeah, this is coming from there. It's like a partial compensation kind of thing. Um, okay. Now, uh, what I mentioned earlier, is there any way to achieve this magnitude transition? Short answer is simply no, right? I think the supernova theory sector has to dig in a bit and to realize this. But yeah, there are no good solutions in the literature, I would say, that would work. Here we have tried a tweak non-minimally coupled scalar field. This is from Wolf et al., the non-minimal coupling paper. I believe he presented in CosmoVerse a few weeks back, so people might still remember it as of now. What essentially happens in this model is that there's a scalar field which couples to the Ricci scalar, and essentially what it does is it modifies the Poisson equation. So this is the Poisson equation here, and what we can see is that there, instead of the gravitational constant Gn that that's we use daily, there's an evolution of the G effective as well. So on the left, I have a plot from his paper. This mu is not the absolute, is not the distance modulus. It is this mu mg, the modified gravity mu, which affects the clustering of the matter. And this is what they get when they combine with BAO, CMB, and uncalibrated supernovae in that case. So what they saw is that there's an evolution of mu, or in some sense you can think of it as effective gravitational constant. So what we tried was, let's say we have this model, and then there's this G evolution in that model, right? The gravitational constant. Again, there are many models in the literature which propose some supernova magnitude transition, but I think physics for all of them remains uncertain. And just to be agnostic of all such models, we just played around with a very simple toy model where we assume that the Chandrasekhar mass and hence the supernova peak supernova luminosity, they vary with the power law in G. So that ultimately gives us a log dependence on the absolute magnitude, right? And so this mu is the mu mg again. So this is how the Z dependence work out. So in this, there are only two free parameters, M, E, and N, the index. And then mu mg is derived from the theory itself, depending on the best fit parameters. Again, we implemented this model, and then we done a fit in the same way as earlier. And this is what we get. So as you can see, first of all, there's a gradual transition in this model, right? And then the fit is not that great as compared to like -40 values that we are getting with the toy model, but it's also not as worse as with only expansion history modification models. So it lies somewhere in between, happening due to partial compensation. I think one of the reasons is that the transition redshift in this model is not very low, right? So the transition starts happening approximately where the dark energy starts dominating, which is redshift 1. And so since this is not a very low Z transition, hence we believe that the transition is, or the fit to the data is not as like delta chi-square is not -40, but somewhere in between. Okay. And then as a final step, as a final check to just remove our dependence on the data set itself, maybe what the analysis we have done is very specific to Pantheon plus shoes. We also tried folding in the surface brightness fluctuation distance measurements. At a zeroth order, the way they work is that there's a pixel to pixel variation in the unresolved stellar light of the stars, and that variation depends on how much farther they are. So once you have calibrated them, we can actually get a handle on what are their distances, right? So here's a plot from the Jensen et al. 2025, from which we also get the sample of SBFs, and this is essentially how they look like. So this is a clean fit to the Hubble law, V equals H naught D. So on the y-axis we have velocities, on the x-axis we have distances, and this is how it looks like. And this is the current measurement. So the systematic errors are small, but okay, I think this is flipped. So this is statistic and this is systematic. The systematic errors are larger. Statistics ones are still competitive what we have, and these are samples extended to very low redshift of 0.02. So these samples by themselves do not have any magnitude dependence. Maybe that goes into the calibration, which we didn't take into account, partly due to the fact that these were calibrated by completely independent JWST plus TRGB samples. And the punchline is, so I'll go quickly over this. If you don't include the 0 point uncertainty, in some sense, if you ignore the systematic uncertainties, then we see that we have a major Hubble tension, because if the measurement is just 73.8 plus minus 0 0.8, and this is not sourced from some absolute magnitude difference, right? In that case, the first the first part of our table, our delta chi-squares change massively from what I showed you earlier when we didn't have SBFs, right? So -1 Each step improvement now went to -15, and this number was -40, which went to -31, right? But the issue is that the 0 point uncertainty is kind of big, right? And you have to include it correctly. And once we do that, the zeroth order thing we can see is that this error bar combined is large. So there's no really a major Hubble tension if you just consider the SBF dataset. And accordingly, it is not able to change our conclusions that much from what we are getting if we don't include the SBFs, right? So the punchline is that SBFs at the current position cannot rule out the M transition type solutions, but they still remain an interesting probe. If the astrophysics get better and we are able to somehow reduce the 0 point uncertainty, we can say that the Hubble tension also arises not just because of Manson plus Shu sample, but you can see them in these samples as well. Okay. I'm not sure how much time do we have, Enrico. Is there time to go over one slide, or can I just skip to the summary?
No, I think you can go on for a few more minutes.
Okay, yeah, okay, that's fine. Yeah, this is the last slide. So, yeah, as I mentioned, we have some interesting things in the appendices as well. And I think this one is important to cover. So, yeah, this one I find the most interesting, or maybe it's a tie, but yeah, this one I feel like there's a need to convey this. So, in this analysis, we have used the complete data sets. We have not, except for the CMB compression, we have not used any proxy data sets, right? So, we have used full Pantheon plus Shu sample. But when we were going through many of the papers related to this, we found that it's very common in literature that instead of using the full shoe sample, what people do is that they can use this some M prior, and then we assume that our job is done, so we don't need to account for the shoes data. You can do that, but there is some care which needs to be taken. So typically how it works is what they use is that they use this M prior, this number -19.253 plus minus 0.027. Now a certainty about that number is derived from Pantheon plus Schu's analysis. And what they do is they consider low Z calibrators along with supernovae up to redshift 0.15. They do this. They truncate it at 0.15 because they don't want to mess up with the high Z cosmology. But at the same time, you need some supernovae to build up a significance good enough or to shorten the error bars to on H naught, and consequently you get a measurement of M. Now the issue is if you combine this M prior with the whole Manson plus Schu's data, you are effectively counting these supernovae up till redshift 0.15. You're double counting them, right? So what is the right prior to use? This is the right prior which was found by Camarena and Mara in 2021 through a demarginalization process. We believe, and even after that, I think many papers used the first prior here, which is in red. And as you can see in this contour plot, in the black we have the complete data. In the red we have with the first M prior which you directly get from the Pantheon plus Schu's paper, and the second one is this one which is obtained from the demarginalization process. And you can see that if you use the red one, then your error bars are slightly shorter, which is again coming from the fact that you're double counting information. So the right prior to use is this one. Okay. So yeah, this was my final slide. I'll just quickly jump to the summary. The only type of late time solutions that work for Hubble tension have to do one of the following things. Either they have a late time transition in the absolute magnitude M. There's a late time transition in absolute magnitude M along with a modification in expansion history. Or the third one, this case we didn't discuss because again it's widely discussed in the literature. Uh, that is, you violate the distance duality relation itself. Again, this is not trivial to do. It requires a massive violation of JR. But if you want to see a few examples, then I think you can see this paper by Teixeira, which is in PRD. But yeah, that's all. That's all from my side, and I'm happy to take any questions. Thank you.
Right, thank you so much, Prakhar, for the presentation. Interesting.